In the world of mathematics, there are few concepts that are as intriguing and as fundamental as the one we're about to delve into today. Welcome to this short video on integration. Now, I'm assuming that you've already learnt this topic in school, and all you're looking for is a quick bit of revision, a little prompt as to what are the key skills involved. So the idea is that I've presented a multi-level, self-marking, instant feedback exercise for you to have a go at. And if there's anything you've forgotten, you can click back into this video and remind yourself. And as you're working through the exercise, remember that integration is more than just an operation. It's a valuable tool for finding the area under graphs and the reverse operation of differentiation. Moreover, it plays a critical role in physics, engineering, economics, and many other fields. You can use it to work out the distance travelled given a speed-time graph, or the result of a situation represented by an economic model. So let's begin with the most basic form of integration, the indefinite integral of a polynomial. What we need to remember is that integration is the reverse operation of differentiation. So when we differentiate, we reduce the power of x by 1. So when we integrate, we have to increase the power of x by 1. So x to the 7 in the first term becomes x to the 8. Now, if we were to differentiate, we would get 8x to the 7, but we want 5x to the 7. So what we'll do is we'll divide by that 8 that we don't want and put in that coefficient of 5 that we do want. So the first term becomes 5/8 a to the power 8. The second term, similarly, let's start off with the power of x, increase it by 1, and then we don't want that 5 when we differentiate, so we divide by it but multiply by the 3 that we do want. So that's the second term. And then the third term, imagine that x after the 8 is x to the power 1. The convention is that we don't need to write down the 1, of course. So if we increase that by 1, we will get x squared. Of course, we don't want the 2, so we have to divide by the 2 but multiply by the 8. So altogether that's equivalent to multiplying by 4. And of course it's negative, as we can see from above. The 26 at the end, you can think of it as 26x to the power 0. So we want to increase that power by 1, so it turns into just x to the power 1. And we've still got that 26 and it's positive. But there could be a number term, a constant term at the end of this expression that when you differentiate disappears. So we don't know what that number would be, so we put in a c. That stands for a constant of integration. It could be any number because it would still give us that expression in the integral sign above. So that is what you get when you integrate that polynomial. Okay, have a go at level 1 of the online exercise and then come back here when you're ready for level 2. Right, well, we have some fractions here in level 2. So the first thing I'm going to do is write them out using negative powers. So you really need to know your indices well in order to do this. So the integration becomes that. Now I can do just as I did before, integrate term by term by increasing the power by 1. So if you increase negative 6 by 1, you get negative 5. But we don't want that 5 in the differentiation process, and we don't want that negative sign either. So we'll counteract it by putting that as the coefficient. Then the next term is going to be x, increase minus 4 by 1, you get minus 3. But we don't want that 3. We do want a 2, and we're getting a negative sign coming out that we don't want, so we need to balance that by putting a negative sign here. And finally, that last term, as you saw from level 1, turns into minus 7x, and then don't forget the constant of integration at the end. Have a go at level 2, and then come back here when you're ready for level 3. Now this is called definite integration because we have 2 limits. So we're finding the area under this curve between the x values of 2 and 1. It's called definite integration. So here we go. We'll integrate it as before. Increase the power by 1 and then balance it by undoing that 5 that would come out as a coefficient. Then the next term, minus 5x cubed, would be 5x to the 4th over 4, and that 8 would be 8x. But we haven't finished yet because we need to evaluate that between the limits of 2 and 1. Now this means you have to substitute 2 into that expression and then subtract what you get when you substitute 1 into that expression. So putting in the 2 to the power 5 is 32 out of 5 minus x to the power 4 is 2 to the power 4 multiplied by 5 divided by 4 is 20. And then substitute the 2 into that minus 8x term will give you minus 16. So that's those 3 terms when 2 has been substituted. And now we need to subtract. And just so I don't forget I'm taking this away, I'm going to put the whole next bit in brackets. And then I can just concentrate on substituting the value of x equals 1, the lower limit, into that expression, which should be a little easier. 1/5 minus 5 over 4 minus 8. So I should put my equal sign here. If I evaluate that, and you could always use the calculator to help you, bit of a nasty calculation there, but it turns out to be 411 over 20, which is equal to, as a decimal, 20.55. So that definite integration, the area under that curve, works out to be minus 20.55. Have a go at level 3. Come back here when you're ready for level 4. Okay, this integral involves a square root and an odd index there, 2/3, x to the power 2/3. So to make life easier for myself, the first thing I'm going to do is write down the root of x as x to the power 1/2. And this stays as it is, x to the power 2/3. And I'm integrating that with respect to x, so that's equal to, okay, increase the power by 1. And then balance out the coefficient that would come down from differentiating that, and the fact that I don't want it there, I'll multiply by 2/3. So when you multiply 3 over 2 by 2/3, you get 1, which is the coefficient of root x that I'm looking for. Okay, the next term, let's increase this by 1. 2/3 increased by 1 is 5/3, and then I don't want that when it comes out to be a coefficient. And then let's not forget the constant of integration. And that's what you get when you differentiate that expression. Have a go at level 4, come back here for level 5. Right, for level 5 we're going to be integrating some special functions. And don't be dismayed because when you come to do the exam, you get the formula book, and these standard integrals are given in the formula booklet. So when you differentiate e to the x, you get e to the x. So it means that when you integrate e to the x, you're going to get e to the x plus that constant of integration. So there are the other standard integrals that we'll need for this level of the exercise. And as you can see, it tells you that when you integrate cos x dx, you'll get sine x. So this is going to be equal to sine x. And then the next bit is easy, because when you integrate e to the x, you just get e to the x. Let's not forget the constant of integration. That's all there is to it. So the questions in the exercise at level 5 will get a little more tricky, but that's the basics of it. Have a go. If you get stuck, talk to your teacher. Otherwise, come back here when you're ready for level 6. Okay, well, I've said it before that in order to be good at integration, you first need to be good at differentiation. Now, if you saw this expression and you were differentiating, you'd recognize this as something you could do with the chain rule, because the inside of the brackets is a little function that you could differentiate by itself. So you could set up the chain rule to differentiate this more complex function. So this level 6 involves doing the chain rule backwards, so to speak. So let's see, let's just use a bit of initiative to say that, well, 3x minus 1, if it ends up to the power 5, it must previously have been to the power 6 before it was differentiated. But then when I differentiated it, I'd get that 6 coming out that I don't want. But from inside the brackets, that little inner function, I'd also get the 3 coming out. So 3 times 6 is 18, which I don't want. So what I'm going to do is I'm going to divide this by 18. Add on my constant of integration. Job done. That's level 6. Come back here when you're ready for level 7. Right, so we're going to integrate this now using partial fractions. The integral of this expression using partial fractions. So the first thing we do is we say, well, this expression that we're being asked to integrate, well, the denominator could be factorized like that. So now we could split this up into 2 distinct fractions. And now if I multiply both sides by that denominator, I'll just be left with x minus 9 on the left. On the right, the first term will become a lots of x minus 3, and the second term will become b lots of x plus 1. Now we need to work out what the a and the b are. X, of course, can be any value, so let's choose x to be a value that suits us. So let's say when x is equal to negative 1. I've chosen negative 1 because that will make that second bracket 0. X plus 1. So if x was negative 1, x plus 1 would be 0, so there'd be no letter b in our expression. The left-hand side, if x is negative 1, would be negative 10. And the right side, it would be a lots of, x is negative 1, so that would be minus 4a. And from that, we can work out that a is equal to 10 over 4 or 5 over 2. The other convenient value is x is 3, because that will make the bracket multiplied by the a 0, so I'll only have b's in the expression. So when x is equal to 3, I'll have minus 6 on the left side, and on the right side I'll have 4b, which implies that b is equal to negative 6 over 4 or 3 over 2. So now I can write my integration using the values of a and b that I've just worked out, and have the integration of two separate fractions which I can do independently. So my integration becomes a over x plus 1 turns into 5 over 2x plus 1 minus the b over x minus 3 becomes 3 over 2 lots of x minus 3. And from the standard integrals we can see that these turn out to be log expressions when you integrate them. So the first one will be 5 over 2 natural log of x plus 1 minus 3 over 2 natural log of x minus 3 plus a constant of integration. Now, the way that this is done in the online exercise, because there are so many different ways you could write the answer down, the pattern for the answer is already inserted into the answer box, and for most of them it's given as a single log function, natural log function. So how would we turn this into a single log function? Well, the key is that when you're subtracting two logs, and of course we are subtracting them here, that is the same as dividing the contents of the log function. So this could be written down as a single log function as the natural log of, and we put the modulus sign to make sure we get a positive value, x plus 1 to the power 5 over 2 over x minus 3 to the power 3 over 2 plus c. Just got that in there. Doesn't look very beautiful, but that's what happens in math sometimes. Okay, that's level 7. And that is using partial fractions to do an integration. Okay, we now come on to level 8, which is using a substitution. So you're either given the substitution in questions, or you have to work out what the inner function is that you can work with, and you get that with experience. So what I'm going to do is let the inner function be u, and it's going to be that exponent there, that 1 minus x squared. So let's see, if u is equal to that, well then du by dx is equal to minus 2x. I've just differentiated that, and I can rearrange that to make dx the subject. So I get du over minus 2x. Now what I want to do is I want to integrate that. Actually, let's say I think the questions are all definite integrals, so let's put some limits in here. Let's say 1 and 0, and let's say we want to do this definite integration. I can now write it down as the integral of x e to the power u, because I've made that substitution, and then my dx becomes du over minus 2x. Now, the limits of the integration, in the original question, they're in terms of x. So the first one is when x is 1. So we can see from our substitution here that when x is 1, u is equal to 0. And the other limit, when x is equal to 0, if we substitute it into here, we can see that u is equal to 1. So it turns out that we're now integrating between 0 and 1, like that. Okay, the nice thing is now that those x's will cancel. Let's bring that minus 2 out of the front and make it minus a half. The integral between 0 and 1 of e to the u du. How easy is that? So that's equal to minus 1/2 e to the u, that's what that integrates to be, between 0 and 1. So that's equal to a half, lots of, substitute the 0, e to the 0 is 1, and then substitute the 1. So the answer is e minus 1 over 2. That's level 8, an example of level 8, integration by substitution. Okay, are you still with us? Let's go on to level 9, where we're going to integrate by parts. Now the way I remember this is remembering what the product rule is for differentiation. If we're differentiating two functions, let's call them u and v, we get, and this is in the formula booklet, that the differential is that. So what I could do is integrate both sides of that with respect to x. So if I integrate the left, I'm just left with the uv, I undo the differentiation. And then if I integrate the right, well, I'm writing it in shorthand here, missing out the sort of the dx, I will get that. Now if I rearrange that and make this the subject, I have got what we call the integration by parts formula. So let's see, in this expression here, I'm going to let u be my x. So I'm going to write that down. U is equal to x. That is the first part of the expression that I'm integrating. And if so, well, u dashed, if I differentiate that, I just get 1. Now I'm going to let my v dashed be sine 3x. So if I integrate that to find out what v is, I'm going to get minus cos 3x over 3. So now my integration, it's going to be uv, which is minus x cos 3x over 3, and then minus the integral of minus cos 3x over 3. So I'll just write that out again and then do the integration. So that becomes plus sine 3x over 9. And now I'll write it down as a single fraction, sine 3x minus x cos 3x all over 9. Phew! That is an example of integration by parts. It takes a little bit of experience to know from your original expression which part of it should be the u and which part of it should be the v dashed. Have a go at level 9. If you get stuck, see your teacher. Hopefully that was just a quick reminder. Come back here for level 10. So here we have level 10. This is using technology, in particular the graphic display calculator, to actually work out some integration questions. So here, by way of example, I've chosen these two graphs here, a quadratic and a straight line, and the question involves finding the area between those two graphs. So it looks like that purple area in the diagram, but what we'll do is we'll go to the calculator and we'll go to a graphs page, and then we'll type in the two graphs so that we can see them on the screen. Change the scales on the axes slightly so that we can see them clearly. And what we need to do now is find out the points of intersection, because those will become the limits of our integration. So it turns out that the leftmost limit is -2 and the right limit is x equals 1. So those are going to be the limits we use for our integration. And what we can do is say that the area under the graph, we can actually write it down as a single integral. It's the graph that's uppermost, which in this case is the 2x plus 4, and then we're going to subtract the graph that's below, which is x squared plus 3x plus 2. We're going to integrate that with respect to x. To be on the safe side, you could always put the modulus sign there to make sure you're getting the positive value. And there's a couple of ways that it can be done on the graphic calculator. We could use the bounded area function, and as you can see, it works out that the area is 4.5 square units. Or we could go to a calculator page and type in the integral between 1 and -2, and this numerical integration function also gives us the answer of 4.5. Okay, now it's your turn to have a go at the online exercise. Don't forget to press the check button regularly as you're working through the questions to see if you're getting them right. And if you make a mistake, have another think and correct your answer, and then press that check button again. Don't forget to claim your trophy when you've got to the end. And there are lots more activities on the Transum website for you to have a go at to improve your mathematics, and you can claim hundreds of trophies. So, what are you waiting for? Get going. Bye.
You can find Transum Mathematics at www.transum.org, where you're welcome to use all of the activities absolutely free. Or jump in with both feet and become a Transum subscriber.